K nearest neighbors. K nearest neighbors, or KNN, is an example of supervised machine learning algorithm. KNN is a simple, easy to understand, versatile machine learning algorithm. It can be used actually both for classification to classify a categorical outcome and also for regression to estimate a continuous variable or outcome. KNN is used in a variety of different applications, such as in finance, in healthcare, in political science, in handwriting detection, and also in image and video recognition. The k-nearest neighbor algorithm is a non-parametric and lazy learning algorithm. Sometimes it's called a lazy learner. Non-parametric means that the algorithm does not make any assumptions about the underlying data that it is working on. It doesn't make any assumption about the distribution of data, or for example, whether the data set is linearly separable or not. So that means the model structure is determined not by prior assumptions, but from the data set itself. This can actually be very helpful in practice because most of the time the real world data that we're working on do not necessarily follow any mathematical or theoretical assumptions. On the other hand, the KNN is also called a lazy learning algorithm. It means that it does not learn a discriminative function from the training data, but instead it memorizes the training data set. A lazy learning algorithm does not need any training data points for generating the model. All training data are used in the testing phase instead. This makes the training a step faster and the testing phase is slower and also costlier. Costlier means the testing phase, it's going to be take more time and gonna involve or require more memory. In the worst case scenario, the KNN method would need more time to scan all the data points that we have in the testing phase and compute the distances of the new data points from the training data points, which is going to be time consuming and also require a lot of memory. In the KNN approach, the predicted outcome for an observation is based on the k nearest neighbors, or the k most similar observations from the training set, where similarity is measured with respect to the set of input variables or features. An important aspect of effectively applying the KNN algorithm is the selection of the features on which we base similarity or distance. An example of distance is the Euclidean distance that we are all familiar with. So let's see how the k nearest neighbors work. Suppose P1 is the point we want to classify using the KNN method. First thing that we need to do, we need to find the k closest points to P1 and then classify by the majority vote of the k neighbors around P1. For finding the closest similar points, we find the distances between the points using measures such as the Euclidean distance, Hamming distance, and Minkowski distance. Overall, classification using the KNN method includes the following steps. Step 1, calculating the distance. Step 2, finding closest neighbors. And step 3, voting for labels. So for example, to calculate the distance, because we need to figure out the closest neighbors, so we need to find the distance of every data points in our training data and the new data points. And after we find the closest neighbors, the k closest neighbors, the classification is going to be according the majority of votes of those k neighbors. The parameter k in the KNN algorithm is a very important parameter. The value of k can vary in the range from only one neighbor, to n, the whole size of the training data. Setting a smaller values for k would make the model more susceptible to noises in training data, while larger values of k would make the model to fail in capturing and detecting the real relationship between the features and output class. So it's important to find the best values for k. The best values of k, we can show it by k star, can be determined by building different models for different range of k's, and then selecting the value of k star that would result in the best model, which is a model that has the smallest classification error. So generally in practice, instead of ranging k between 1 to n, we would range it from 1 to a square root of n divided by 2. Data scaling, and specifically normalization, is a common practice in machine learning, and specifically for KNN algorithm. Before computing the similarity or the distance between a new observation at the test data point and the observations in the training data, it is a common practice to normalize the values of all variables. By replacing the original values of each variable or feature with the corresponding z-scores, if you remember from the statistics, we can avoid the computation of the Euclidean distance being disproportionately affected by the scale of the variables or the features. Let's see an example of an application of KNN in classifying a categorical outcome. Suppose a bank would like to see or predict, classify that based on their data that they have, whether a client is a loan default or is not a loan default. A loan default is a client or a person that would fail to repay the loan according to the conditions and terms that they agreed to. So the bank has gathered this information. They have the average balance of their clients and also their age. Based on this, they want to see, also they have, this is the training data, so they also have whether the person, the client, is a loan default or not. The loan default, 1 indicates that the person is a loan default. That means they failed to repay their loan according to the terms they agreed to. And 0 means that no, they actually were able and capable in repaying their loan. So this is the training data that we have, and the bank now would like to make a model, make a prediction, a classification on a new customer that they have based on their average balance, two features, average balance and their age, to see whether they would be a loan default person or not. So we have 10 observations here. This is going to be our training data. And the bank would like to classify a new observation or a new applicant with an average balance of $900, and his or her age is 28. So here we want to use the KNN algorithm to make prediction or classification based on these two features, the average balance of $900 and age of 28. The first thing that we need to do before applying the KNN algorithm in this problem is to normalize our data. So we have 10 observations in the training data set that we have, and we have two feature variables. We have the average balance of the clients and we have their ages. So we need to find the average and a standard deviation of these 10 observations based on these two features, and then instead use the z-scores values instead. So we have done that here. We have found a z-score for all the 10 observations based on the two features, and we have plotted on this scatter plot right here. The average balanced z-score after normalization is shown in the x-axis here, and the age z-score is shown in the y-axis here. These are the 10 observations that here we have. The label or the classes of these observations, if they are lone default, is shown by the black circle here that you see, and if they are no default, then they are shown by this white circle here. And this little red triangle is actually our new observation that we want to make a prediction for or classify to see whether it is a lone default person or a no default person. So this is visualize, and if we consider the distance as a Euclidean distance that we are all familiar with, then it's easier to classify this new observation using by eyeballing. For example, if we consider k equal to 1, then the closest observation or closest neighbor to our new observation would be data point 2, which is a lone default person observation. So we would actually classify our new observation as a lone default. Or for example, if we consider k equal to 3, then the three nearest neighbor to our new observation is these 3 points. We have data point 2, 6, and 7. 2 is a lone default, and 6 and 7 are both no default. So the majority of votes here would be 2 to 1, and we would actually classify our observation as a no default person. And this is very clear. But sometimes actually it can be challenging. For example, if k is equal to 2. So if we have if we only had to use two neighbors here, then the closest is not a fair circle, but the closest observation to our new observation is these two data points, data point 2 and data point 7. So here we don't have a majority of vote. 50% are lone default and 50% are no default. So we need to have a cutting point. We need to have a cutting point. And for example, 50% would be cover cutting point. If we consider 50% our cutting point to classify it as, for example, lone default or no default. So we need to specify at what point we would classify, if it's 50-50, what would it be classified as to. Using different K, we can get different output and prediction for the new observation, as we saw in the previous example. And also we need to use a cutting point here, 50%, to be able to make a prediction when it's 50-50% the votes. So this table here shows that with different Ks, the output of classification for the new observation. For K equal to 1, the percent of classes of one neighbor, or the lone default neighbor, is 1. So we are going to classify the new observation as lone default. And for 2, we saw that we need to have a cutoff point, 50%. So we would classify it as a 1 class. And you can see it for k equal to 3, 4, and up to 10, which n is equal to 10. The total number of observation in our training data set is 10. So as you can see here, k, the number of neighbors, can vary from only one neighbor, to 10 neighbor, the total data points that we have in the training set. So understanding the application of a KNN method for classification is pretty straightforward. It's very easy to understand, but is it possible to use KNN methods for predicting a continuous outcome instead of a categorical, which is a classification algorithm? Try to think about it, and if so, how can we do that? We're going to answer this question later on in the course. Now let's see an example of application of KNN in estimating a continuous outcome. This is called regression. So we want to use KNN for a regression estimation. Suppose that we have the same data that we had previously. So we have 10 observations with their average balance and with their age. So we would like to estimate the average balance. That's our target variable now. It's a continuous variable. We want to, based on the feature variable age, we want to make a prediction on the average balance. So we have a new observation. His age is 28. We want to use KNN to make a prediction on his average balance. So these are our data, the average balance, which the target variable is in the second column, and the age, the feature variable as a predictor, is on the third column here. So because we only have one feature variable, independent variable predictor here, so we can actually plot our data on only one axis, on the x-axis. So here, the x-axis shows the age of the observers, the clients or the customers. Since the smallest or the youngest customer or client here is 26 years old, the ages start from 25 and it goes to 60, the x-axis. 25 and 60, and we have our observations spread around based on their age. So the location in this x-axis shows their age, and the number that you see on top of these little circles, it's actually their average balance, and this is our new observation, and we want to make a prediction based on its location, which shows its average, it shows its age, using a KNN algorithm. So for example, for k equal to 1, let's see how this works. For k equal to 1, the closest neighbor to our observation is this little circle, which has an average balance of 36. So that's going to be our prediction for the average balance of our new observation, the red triangle observation. His age is 28, so we would make a prediction for his average balance to be 36. Right. So let's see how it works for a higher uh, number of neighbor. So if k, for example, is 2, I'm going to go with k equal to 3. Suppose k is equal to 3. Then the 3 closest neighbor to our observation is the 3 data points. So what we can do to make a prediction for the average balance is just to find the average of these three balances. So it would be the average of $671, $36, and $2,100, which would be about $935. And we can continue this with so on and so forth until n is equal to 10, the size of the training data sets, the total number of observation in our training data set. So this would be our observation. Based on different values of k, the number of neighbors, we would come up with different prediction for the average balance of the new observation here. So it is listed here in this graph right here. So for when k is 1, one neighbor, our prediction for its average balance is 36. For k equal to 2, actually we have a tie here, and this is the problem that you see here. So the distance between our new observation age and the previous data points is actually, this is the age of this person is 26. So the age of our observation is 28. So there is 2 years difference between these two. Also, the distance between our observation on this x-axis and this point right here, which is age is 30, is also 2 years. So there is a tie here. These 2 data points, this one and this one, are in the same distance from our observation. So when we want to go with k equal to 2, because we have a tie here, we have to include both of them. So we're going to have to actually, that means that we're going to have to consider 3 data points here. So we're going to include all of these 3 points here. and then find the average balances of them, and that would be 936. So that's why you see for k equal to 2, you see 936 because we have a tie here. So that's our prediction. Also for k equal to 3, we are still going to make a prediction of $936 as the average balance. For k equal to 4, our estimation of the average balance is 750. And as you see here, and as we increase the number of neighbors, our prediction for the average balance is increasing here, as you see here. So here we want to talk about the characteristics of the KNN algorithm, starting with its advantages. As you learned, the KNN is a non-parametric algorithm. It means that it makes no assumption about the data that it works with. And this is a good thing because most of the time when in real life we want to apply a model on a data, we don't know usually much about the data. We don't, for example, know about the distribution of data. So this is a good thing that the KNN does not make any assumption prior to working with the data. So it builds itself after it learns about the data. The next thing about the KNN is that it's very easy to implement, as you notice here. It doesn't have a lot of steps or even parameters. You only have one parameters and a pretty straightforward algorithm to implement. As we talked about it earlier, KNN is an example of a lazy learner or lazy algorithm. It means that it does not have any function to learn with the data. So generally, it has a rather faster learning process. Although for the application, it has to actually compute the distances or the similarities of any data points to its training data, and that can be time consuming and also memory consuming. We haven't noticed this here because so far we have worked with a toy problem, like a small size problem, but in real application, you will be notice this. Let's now see the disadvantages of the KNN algorithm. The first one is called the curse of dimensionality, and it's a common problem with a lot of algorithms. And what it means is you might have an algorithm that works well and perform well on a small size data or even medium size data. But the problem is when you want to work on larger data, your algorithm is going to disappoint because it cannot perform well on large size data in high dimension. And this is specifically true for KNN algorithm because of its nature, because KNN works with the idea of nearest neighbors. So that means that it has to find the distances between different data points based on different features. So if you have high dimensional data, that's going to be a lot of computation. It's going to potentially hurt the algorithm. And also it's going to be required a lot of memory because KNN algorithm has to memorize and store all the training data points so that it can compute the distances for every new data points for every feature of the training data sets with the training data points. And also that means a lot of computation. So it has to process a lot of, it requires a lot of processing, and that's going to make it computationally expensive. Uh, the other disadvantage of KNN algorithm is again a result of its nature, which is has to compute the distance between different data points based on a feature. So if you have categorical features, for example, how would you find the distances between them? That would be difficult and challenging. So for example, we are able to find the distance between real values or any feature variable that are real values. For example, it's easy to find the distance between 10 and 5, but how you would find the distance between or find and define the distance between categorical features such as a color. What is the distance between yellow and green? Or what is the distance between a type of car or brand of car or brand of phone or any other categorical features?